All right, hello guys. Today we're going to talk about some different ways that you can factor polynomials. We know that if they're in factored form, they're really easy to graph. So if we're given one in general form, we want to be able to switch that to factored form. A couple of different tricks that you can use are really factoring methods that we already know from factoring quadratics. The first one is that you can try to factor by grouping. That was, remember, if you have 4 terms here, we can look at just 2 of them at a time and factor those. So in these first 2, they have an x squared in each of them. So I can take that out. And then what will I have left? There'll be an x right here plus a 2 right here. Now I'll look at my second 2 terms. What do these both have in common that I can divide out? I can divide both of them by -16, and then I'll have an x left plus a 2. Now I can see that both of these have an x plus 2, so I can take out the x plus 2, and then what do I have left? X squared minus 16. Still have my y equals out front. This is closer to being factored, but I can actually do more now. Now that I have a quadratic right here, I know lots of ways to factor quadratics. So I know that when I have an x squared minus a perfect square, that's one of those special situations. So I know that x squared minus 16 is going to factor to x plus 4 and x minus 4. If I multiply these 2 things together, I'll end up with a minus 4x and a positive 4x, so that gives me that 0 in the middle, and a negative 16 on the end. Now I have this factored all the way. I can see that my roots happen at -2, -4, and +4. And if I wanted, I could even sketch a graph now of this. Here are my roots. I have a leading coefficient of 1, so that's a positive number, so I know I'm going to end up here. And I can put in my graph. All right, let's try one more factoring by grouping problem. If you want to pause it and try this problem yourself, feel free to do that. So again, I'm going to look at just the first 2 and then just the second 2. On the first 2, they have an x squared in common, and then I'm left with x minus 3. On the second part, they're both divisible by a positive 4. So I'm going to have my plus 4, and I'm left with x minus 3. My parentheses match again, so I can pull out an x minus 3, and then I have left x squared plus 4. This time, I have the sum of squares, which is not nearly as fun as the difference of squares. This is not going to factor any further. This is where I have to end my factoring. I can, however, still find the roots of this thing. My roots come when either x minus 3 equals 0 or x squared plus 4 equals 0. So I have one root at 3. Over here, x squared equals -4. If I take the square root of that, I have plus or minus the square root of -4, which is really plus or minus 2i. So the 3 roots of this graph are at 3, 2i, and -2i. So I have found all 3 roots. It was degree 3, so I knew there should have been 3 of them. Here they are. If I want to graph this one, I know I have a root at 3. I have a positive leading coefficient, so I know this is going to somehow do something that goes up on the right and down on the left, and I can't see those imaginary roots anywhere. If I really want to have a good idea of what the graph looks like, I have to do more plugging in of numbers and plotting other points, because there could be other wiggles in here, but this is the only place where it's going to cross the axis. Another trick that I can use to factor polynomials is to see if it's kind of like a quadratic. So here we have something that's the 4th degree, and then I have a squared term and a constant term, and that's all I have. I can do a tricky trick where I say, let's let a be equal to x squared. I just picked a letter, a. Doesn't matter what letter you pick. If this is true, then I can rewrite this as a squared, because that's equal to x to the 4th, minus 4a plus 3. That's not going to change. Now I have something that's really a quadratic. I know how to factor quadratics. This is an a and this is an a, and I need factors of 3 so that I get a negative 4 in the middle. So I want a minus 1 and a minus 3 right here. Now I have to remember, though, that I don't really want a. I want to put my x's back in. So this is really x squared minus 1 times x squared minus 3. This one is my old friend difference of squares. So I know that I can rewrite him as x plus 1 and x minus 1. This one, although it's subtraction, is not a difference of squares. It's not going to come out nicely, so I'm just going to leave it in this form. So here is my factored form. So when I want to find my roots, again, I can set each one of these sets of parentheses equal to 0. I'll get a negative 1 from the first set, a positive 1 from my second set, and from this third set, I'll add the 3 over. X squared equals a positive 3. X equals plus or minus radical 3. So I have a root at a radical 3 and at negative radical 3. Here are my 4 roots all listed out. I knew there should be 4 because that was my initial degree. If I wanted to graph this one, I could. These roots, although they are ugly, are still real roots. These are both nice numbers. We call those rational numbers. Square root of 3 is an irrational number, but all of them are real. So if I were to graph this polynomial, I could put a root at 1 and 1 at negative 1. And I know that the square root of 3 is somewhere between 1 and 2, because the square root of 4 is 2 and the square root of 1 is 1. So this is 1 point something and negative 1 point something. So I'm just going to put those on here. I have a positive coefficient, so I know that my graph will look something like this. I had 4 real roots, 2 of them nice, 2 of them ugly. But there is my polynomial. Let's do one more of those. So again, if you would like to pause it and do this on your own, feel free. I have another secret quadratic if I let a be equal to x squared. So then I'll have negative 2a squared minus 5a minus 3. This one has a leading coefficient, so a little bit more work is involved. Remember, you can do your diamond. Negative 2 times negative 3 gives me a positive 6 up here and a negative 5 on the bottom. So then the factors that I must need are negative 2 and negative 3. So I can rewrite this as negative 2a squared minus 2a minus 3a from this, because that's equal to negative 5a, this minus 3 is still hanging out on the end. Now I'll factor by grouping. Take a negative 2a out of the first two terms. I'm left with a positive a plus 1. Out of the second part, take out a negative 3. I'm left with positive a plus 1. So that means I have negative 2a minus 3 times a plus 1. Let's put our x's back in. So negative 2x squared minus 3 times x squared plus 1. Neither of these is a difference of squares, so this is as far as I can factor it. This is my factored form. If I want to find the roots, I'm going to set each of these equal to 0. So negative 2x squared minus 3 equals 0, and x squared plus 1 equals 0. If I solve this, I have a positive 3 over there, divide by my negative 2. I have negative 3 halves, which means I have the square root of negative 3 halves. I need to make this prettier, so I'm going to take out an I to get rid of the negative, and I have to rationalize it, so I'm going to multiply on the top and bottom by a radical 2, which gives me plus or minus I radical 6 over regular 2. Here are two of my roots. This one is easier to solve. If I move the 1 to the other side, it's a negative 1. Take the square root of that. I end up with plus or minus the square root of negative 1, which is, of course, plus or minus I. So the four roots of this one are I radical 6 over 2, negative I radical 6 over 2, I, and negative I. All of my roots are imaginary. If I try to graph this polynomial, I know that it has a negative leading coefficient, so the ends are both going to be down, and it will never, ever hit the x-axis. I don't know if something wavy happens in there, but I know that both ends are going down. Again, if I really wanted to know what this graph looked like, I would have to plug in some x's to get some y's to go with it. For now, I'm happy to know that it never hits this x-axis, and these ends are going down. So the two methods that we looked at today for factoring polynomials were factoring by grouping and factoring a secret quadratic. These two methods won't always work though, they only work sometimes. So later on, we'll look at some other ways that you can try to factor polynomials. Okay, have a great night, and I will see you in class. Bye.